Hi, I'm Francois Rene Rideau, and I'm here to tell you about orthogonal persistence, the model. So what the hell is orthogonal persistence? Well, let's imagine that you are hacking happily somewhere in a cafe or wherever, and you are hackers, you will program defined functions and variables, but if you are just a user, you could be just opening some documents, Word, whatever. And unhappily for you, your laptop is indefinitely borrowed to help the third world. And of course, at the same time, your data center gets destroyed by random orcs. And so in today's world, that would probably mean you lost a lot of data, days, maybe months of data, and that sucks. But in a better world, you would just go back to a safer place where there are no orcs and no borrowers. And you would call your technical support, and someone would bring you a laptop pre-installed. And if you don't have technical support, you can install it yourself. But once it's installed with the software, you just have to enter your credentials, login and password, and there you go. Everything is back right where you left it. Maybe your laptop has a different screen size, so the window size are slightly wonky because it resizes them, just like if you connect to a different screen. But everything is there. Your functions are exactly where you defined it. And of course, if you were not connected to the internet when your laptop was stolen, you may have lost everything since the last time you were connected to the internet. But as long as you're connected to the internet, everything will be backed up in 5 data centers on 5 different continents, owned or controlled by 5 different nuclear powers. So really, there's no reason you should ever lose any data until the collapse of civilization itself. That's the idea of orthogonal persistence. So what does persistence mean? Persistence means your data survives. What does it survive? Well, whenever someone makes a claim about persistence, just like when they make a claim about security, you should ask, what is your attack model? What is your failure model? Unexpected events can happen. Your battery may die, unexpected power loss, an accident, a hack by the North Koreans or whoever, theft, fire, war. These are unexpected, although the chances of one of these unexpected events happening is non-trivial. It's not expected, but the probability is not trivial. And then there are the expected failures. There's 100% chance that 10 years from now, your laptop will be dead or obsolete, and you won't have it. There's also a 100% chance that 20 years from now, your favorite software vendor will not exist. The version of your software will be long obsolete and not supported. That's 100% chance of that. Will your data survive these events? If it does, that's persistence. If it doesn't, that's transience. What does orthogonal mean? Orthogonal means independent from what the program specifies. That means the programmer doesn't have to persist things, and maybe he even cannot persist things. If he specifies how things are persisted, it's just a happy suggestion at best. But orthogonal means, in the end, it's not the programmer who persists data. It's the system. And so that means that the system programmer can persist the data once, and then it's persisted for all time, for everyone, and one person can persist the data for everyone else. And that's opposite of persistence being reinvented every time by every application, every programmer. This is not a new idea. Actually, in the 80s, there were plenty of object-oriented databases that made Lisp or Smalltalk or C++ or Java or what have you orthogonally persistent. Although they had a flaw, most of them only persisted the data and not the running processes. Although there are exceptions, most notably OIML or Grasshopper or Eros, that did persist the processes, running processes, and not just the data. So when you turn off the computer or whatever, something happens to it, and you turn it back on, not only the data is still there, but the running interaction is also still there, and that's very important. Unhappily, the idiot author of OIML died young, so we know him for L3 and L4, Johann Littke, but he could not continue his work. I Still angry at him for dying young. And also the funding dried in the 2000s. So no more work on orthogonal persistence for a long time, but it is reborn today under the name of durable execution, which is the same thing, except this time we do insist on the processes surviving. And you'll find a lot of academic research recently on this kind of topic, so that's good. As for me, I was introduced to orthogonal persistence by my good old HP28 pocket calculator. It was a pocket calculator programmed in a symbolic language with algebraic expressions. You had a visual stack. It was great. And when you turned it off and back on a week later, the data is still there. Problem, it had no network connection of any kind, no backup. All you had is to change the batteries every few months, otherwise you would lose all your data. And when you change your batteries, you had like 2 minutes or 3 minutes to change them before the data goes away. So it was orthogonally persistent, but the failure model was very limited. Later, I worked on ORMs, and recently I had a vision of how to do orthogonal persistence better, and I will tell you about it. My thesis today is that orthogonal persistence is the right thing. It's the right thing that everyone expects implicitly when they use a computer. And the one thing that makes orthogonal persistence work is when you persist processes, not just data, but running processes. And this is what simplifies everything else. While I'm at it, I will claim that database transactions are the absolutely worst abstraction you want to offer programmers. That is wrong. All databases today are wrong. And finally, I would like to argue that, yes, orthogonal persistence will solve a lot of problems that today are linked to persistence, but there are a lot of problems that remain, except that they will have been decoupled from persistence, and then elevated and restored to what they intrinsically are, and elevated. We'll see that. I also have another broader thesis, which is that orthogonal persistence is economically inevitable, because it will make everyone 100% more productive. But that means it will also drastically change software architecture, it will disrupt existing business models, and it will improve division of labor, which means that it is a great business opportunity today. So what do we have today? Today we have fractal transients. That is, everything is transient at every level. I was traumatized by my mother the first time she used a computer. She spent 8 hours entering books in her catalog of books in the database. She turns off the computer, she goes to sleep. The next day, what happens? It's all gone. No one had told her she had to save the file, otherwise it's all gone. Whoops. And so who here has lost data because they had no backup, or they forgot to save, or had a bad backup, or they lost their backup? Raise your hands. Okay. Who never lost any data because they had... wow, 1%, congratulations. So for me, it's so bad that I have Control-X, Control-S wired in my fingers. You know what Control-X, Control-S is? For you, it might be a Command S or F2. It's the save command. Every time I write a few paragraphs, I save it. That is, I have solved persistence in a lot of cases through wetware. It's like, it's automated, but through my brain. And I will argue that orthogonal persistence is the way God meant it, because if I didn't mean for the computer to remember it, I would never spend the time typing it or telling it to the computer to begin with. The only reason I would ever tell something to the computer is so that it remembers it. Maybe exception if it's a game or whatever, but anything else than that, I want the computer to remember. And then some of you might say, but don't modern apps already solve that for you? When you use Google Docs, it's still there, isn't it? And if I use my phone, I can upgrade phone. Like, it pretty much survives, doesn't it? And kind of, but not really. This is what I would call vendor lock-in persistence. The big vendors, such as Google and Apple, have solved persistence in the easy case. If you do the same thing as everyone does, it kind of solves, but most applications, actually, it's very unreliable whether they solve it or not. And even if you solve it with Google, it's only solved if You keep using the same account all the time, and you don't have to sync between multiple devices. And of course, at any point, Google may cancel your account because it decides you're not politically correct. Happened to one of my uncles. They may cancel their product. The product may change owner, and the new owner may take it in a new direction you don't like. They may go bankrupt. They may upgrade their software to add features that you really hate. Now it adds everywhere. Or they may fail to upgrade their software, and now it becomes unusable because of bit rot. In all cases, your data is hostage. You better pay your bills on time and pray that the vendor remains healthy as long as you need the data. That's vendor lock-in persistence. For developers, persistence is hard mode. Your computer, when it starts empty. Your processes, they start empty. You have to explicitly save and restore data at the right place, from the right place, in the right way, with the right format. And anything goes slightly wrong, it becomes hell. Or there are more than one users or more than one computers, have the format changed, has it been an upgrade, everything becomes hell. Then you have a zoo of different storage abstractions. You have file systems, databases, web services, distributed version control systems. They're all incompatible one with each other. They have very different APIs. Half of their API is actually maintained not through code, but through convention, human convention. And you have to handle all this absurd complexity, fake persistence the hard way all the way. And of course, you won't handle all the cases. So you will leave a lot of mess of data, all like out of sync, slightly wrong data everywhere. And then you need a sysadmin to deal with it. There are hard problems. Now you have lots of copies out of sync. You have 10 copies of the same thing that's old, and you are missing the one copy of the most recent data. You have your backups that are fragile. If you haven't tested your backup, do you really know you can restore? Once studied at a university that's lost its data. No problem, we have backups. Whoops, actually they don't work. There's a schema upgrade problem. You know that sooner or later, you will have to upgrade your data to a new database because it will be so obsolete that it will be unusable. And this will cost you tens of millions of dollars if you're a big company. Whoops. You know it will happen, and you better have these tens of millions of dollars aside when that happens. If you want to federate data or short data for reliability, it's possible. Same thing, tens of millions of dollars. Hard problems. But what if? What if persistence was a default? What if it had no more vendor lock-in? What if developers didn't have to care about persistence? Except maybe the tiny minority of developers who really love persistence, and then they can focus on it and ingest it. And what if these hard problems were made easier somehow? Well, here's what orthogonal persistence would look like for users. Orthogonal persistence would mean your data is just there. It's always there. You typed it. Of course, you meant it to be there. You come back. It's there. Not just your data, but also the processes you launched. They're still there. Your computer fails, no problem. Your Windows, everything is still there. You have started a long-running computation. The computer goes off. The computation resumes for exactly where it left. So you will want to run code in a domain. A domain, think of it as a persistent virtual machine, a container. It is kind also of a subdirectory, but it contains the code and the data at the same time. The two together. You don't lose the link between the code and the data. And of course, you will have domains and subdomains, etc. And in a domain or subdomain, you will run an interaction that will be such as editing the document, but see that it's not the app that controls everything that creates subdomains and subdocuments. No, it's a domain that comes first, and then inside the domain, you invoke the app. It's not the app in control, the domain in control, and the app inside. So it's not an app. And of course, there's a caveat with domains. You must be sure to subscribe to your 5 storage providers on 5 continents, etc. Otherwise, you will lose it. But you know, it's something that will be the default. When you buy the computer, it will come with a service that already does that for you. Of course, if you are an advanced user, you will want to change who are your providers. But really, it's something that should be fairly standard and easy to change for anyone. And if you don't care, you'll find someone at the local shop who will help you with it. And for a few tens of dollars per year, you will have your 5 backups on 5 continents. So pardon the Lisp syntax. This is just really a tree. It means that a domain, you have a main domain, me, and you have a subdomain for work and subdomain for home, a subdomain for your secret agent activity, a subdomain for your love life. And inside your work domain, you'll have things from client 1 and 2 and 3 and HR. And certainly, client 1 should never see anything from client 2. Client 2 should never see anything from client 3, etc. It should remain separate. That's what domains are about. At home, your accounting for taxes is somewhere. Your kid is somewhere cooking somewhere else. Don't meet kids and cooking. DIY, etc. If you're a secret agent and you're a triple agent, you absolutely don't want the CIA, the KGB, and the Mossad to know that you're a triple agent. Absolutely not. And similarly, if you have a love life that's a bit complicated, you don't want your wife and your lovers to know about each other. And that's even if you're honest and there's only one at a time, you still don't want them to know everything about the others. So, and of course, inside the client 1, client 2, there are sub-activities, etc. It goes, this is just the top of the tree. So what it means is that creating a subdomain is not something reserved to system administrators. It's something that regular users will want to do all the time. It's just how you do things. You start a domain, and inside that domain, you do some activity. One important thing about the security of these domains is that whenever you try to copy or share something out of a domain, the originating domain will say yes or no. Like, no, you can't copy this to that. I mean, I'm the CIA, don't tell that to the KGB. And similarly, when someone wants to copy things in your domain, you will want to check that there's nothing malicious, there's no virus, nothing bad. So you will want validation both when you copy data out and when you copy data in. And that should be a deep part of the operating system. It's not your application that can validate anything and that knows everything before it validates it, and therefore it's a big security problem. No, deep in the operating system, you want to have this notion of policies for copying things or sharing things in and out. Of course, domains are also used for resource accounting. So you start a domain with like 10 megabytes of memory or 1 gigabyte of memory, whatever it is, and you can count what takes what memory. And that's important. And what is great with domains compared to what we have now is that since the code and data are together, if you run out of memory, you know what is tied to what. You know what to throw to the garbage or not, because the two are together. You don't have a huge terabyte disk, and you don't know what files serve what purpose and what is linked to what. Of course, you can also do your backup configuration per domain. Probably your work domain will be backed up on work computers and work servers, while your home things are different servers and different backups. OK, activities, you have documents that you interact as well. The important thing is that you don't save things, but you still need to tag them as publishable. That is, not every version of your document is shareable with everyone. If you are a lawyer, you draft a document, you don't want the intermediate data to be seen. You don't want the data that was copy-pasted from another client to be seen. You want only the right versions to be seen. So no save button, yes, tag button, yes, share button. For developers, similarly, you just persist the data. It is always shared. No, it's not always shared. It always persists, but you choose when you share things. You choose who can interact with which processes when. You no more have to save and restore data to get it to and from bytes, to copy and send it. And just that eliminates 30 to 70% of all code. Imagine everyone is immediately 100% to 200% more productive just because they have all that code not to write. And that's from an old study from IBM that said, yes, 30% of the code is just the marshalling and unmarshalling. And it's even worse today. And not the error recovery, nor the selection of where to persist what and which files and which network to persist to and from. No, just the basic marshalling and marshalling is 30% of all code. And just for the variables, then we haven't talked about persisting processes. And another thing that's very important for developers is that their processes may no longer fail mid-invariant. Right now, when you have a process that modifies a file, the process may die at any point. Your file may be corrupted in ways that are unforeseeable, and you have to deal with corruption all the time. But if the system handles the persistence and keeps the data and the processes together, as long as you didn't decide to kill that process, the process will run. And so if the computer is interrupted in the middle of the process doing something to the file, well, it is guaranteed that the process will restart and complete whatever it is doing. And so as long as your process is correct, the file will always be correct and guaranteed, or will be currently locked by the process. And maybe your process is incorrect and keeps the lock forever, but that's on you, on your process for being incorrect. But as long as your process is reasonably correct, it is guaranteed that your files or your data will never be interrupted mid-invariant being broken. That's very important. Capabilities. Now that everything is saved by default, the world changes. Imagine today a photo app. Your photo app needs to be able to open and save files. So any app must now be able to read all your data. The simplest app needs to be able to read all your data. And because sometimes you need to do it over the net, the simplest app now needs to have unlimited internet access. And it needs to download extensions because there are new file formats. So the simplest app needs to be able to download arbitrary code from the internet. Which means that on today's transient systems, any app can compromise all your data. And maybe it cannot become root, but it doesn't matter because it can access all the data of the single user on the computer, so it's just the same as being root. It can do everything. On a persistent system, on the other hand, your app can only edit the picture you give to it. Saving and sharing is handled by the system, which means that your app never has any reason to open a file. Your app has no reason to open the file system or to access the internet or to download code. So, and when you start thinking about that, you think, oh, wow, it's not just for persistence. There are a whole lot of capabilities that can be restricted once you have a system that is reflective and where the system orthogonally handles aspects of the software for you. Wow. And this is, of course, a productivity improvement because when you have all this code not to write, you can focus on the part that you are good at and the part that you're original at and the part that you contribute something new to. It also means that you have fewer things that you get wrong, so fewer bugs along the way to debug. So you are more productive. But that's also a smaller attack surface. Now, there are all those things that the hackers won't be able to do because you wrote less code, so less code can open to attacks. And even better, it means that you can flag whoever reaches for the forbidden capabilities as hostile. If all your code, all your data is saved by default, and anyone who tries to marshal it and send it over the network, you know he's a bad guy. And anyone who tries to write a file, you know it's a bad guy. This program is obviously written by a hacker, by a spy, by a hostile force. You should call the FBI immediately, or the FBI may be called immediately automatically by your software. Any code found on the wild that tries to save a file is obligatory malicious code and immediately sent to the police. And that's possible because persistence is handled by the system. And what is even better, all this is true whether the code is written by a human or an AI. It's not just humans who become twice more productive and twice safer. AIs too become twice more productive and twice safer. Of course, there's also the notion of full abstraction. Now that we've separated the applications from the system, we can make it so the application knows nothing about persistence. and the people who persist know nothing about the application. And if you use types along the way, I know that a lot of people here like types, you can make it so that it's impossible through the type system for the application developer to even write something wrong with respect to persistence. And it can be also made impossible for the people writing the persistence to even selectively do something depending on the data. You can have blind quantifiers or full abstraction that prevents the people from knowing what they shouldn't know. And of course, same thing, the user and the admin can also configure services with the providers, and no one needs to know what they don't need to know, and everything just works fine. When you do your backup configuration, all your data can be encrypted with a use one salt, with one type pad. If you use a whole disk encryption today, it's a two-time pad. The same salt is used for every version. So if a bad guy gets 2 copies of your hard disk, he can see the difference every time between the two and guess what you're writing. But we can have systems where all your backup providers only see encrypted data with a one-time pad, and therefore they can see nothing about your data except how much of it you have and how fast you change it. You should be able to add and remove a provider at will. And of course, I advise you to add a new one before you remove the other one. Otherwise, you have a moment where your reliability is diminished. But you could have lots of independent replicas worldwide, and it could be managed automatically by your management layer in a RAID fashion, like with erasure coding. So you can have if at least 2 of these nuclear powers don't declare me an enemy out of 5, my data is going to survive. And because the data of code and data are together, now you can have a financial layer that tells you something. This application is growing 1 gigabyte every month, but you only have 10 gigabytes for it. So like before the end of the year, you will need to upgrade your subscription. You can have software that automatically helps you plan your spending, and that's possible because your processes and your data are together and not separate, so you can see where you need to spend money. OK, what is the programming model of fractal transience? The programming model of fractal transience is one where, with respect to regular programming languages, everything is transient, especially processes. And if you want anything to survive, you have extremely complex storage protocols. Making anything atomic in any of your favorite programming languages is super hard. And a lot of the persistence relies on wetware convention. That is, this actually works because we only take files from here or there. And this is not enforced by the system. This is totally enforced by human convention of where the file should be and which order you do things. There's no lock, but there's kind of a wetware lock, like don't do things this way or things will fail. So the persistence relies on the wetware. So programming languages are not designed for persistence at all. So when we do want atomicity, etc., what do we use? A database. And databases suck because, yes, they provide you this atomicity that you're almost certain not to have if you don't use a database. But then you have a package deal. Together with your atomicity, you have the worst programming languages ever. Who here has programmed an application in any language except a database with the minimal amount of SQL needed to persist? Okay. Who has done the opposite, writing an application entirely in SQL with a minimal amount of Python or C to run outside the database? Nobody. This has existed. I'm told that some people in Switzerland have done it, but this is an exercise in masochism. There's a reason why people don't use SQL, because it forces you first, this relational data model that is absolutely terrible. No one wants a relational data model in the world. Some people do work with tables. Who? People who use spreadsheets and people who use APL. And I invite you to go to the APL workshop later this week. People who really care about tables, they use spreadsheets or APL. No one in their right mind would use SQL. SQL doesn't have a standardized way to update data. That's how bad it is. And of course, they claim that everything is a table, but the model doesn't work. For example, you still need queues that are not quite table. You still need procedures that are not quite table. So it's a lie. Even inside today's database, everything is a table is a lie. And of course, then you have a horrible evaluation model where half of your program is written in the client, which is actually the server from the end user's point of view, and half of it happens in the server, which is just the database. And they will try to optimize the numbers for the database vendors with speculative evaluation, et cetera, and transactions that have loads of different modes. And that optimizes the numbers for the benchmarks of the databases. But all that does for the end user application is making the code extremely more complex for whoever writes the application without providing any value whatsoever. Other reasons why databases are bad: there's no efficient or effective way to persist your processes or user-defined code. You can do it if you really insist, but it will be extremely hard. You can try to encode your continuation as JSON or whatever and save it in a queue, and that will provide your persistence of processes. Good luck with that. It's possible. I've done it. For user-defined code, you can write, of course, an interpreter, and it will be super slow, but you can have user-defined code. And of course, databases themselves don't persist. The namespace of a database is tied to an IP address, to a machine, to a disk, etc. And these things have a finite lifetime. Your IP address will go bad, your database vendor will go bad, your disk will go bad, your machine will go bad. And then, sure, if you're a big company, you can spend a few millions of dollars to organize a migration. But for most people, you find that the database don't persist. The namespace doesn't persist, just bad. Database don't compose or decompose. Once again, federation or sharding is $1 million problem. And inasmuch as there is security built in those databases, the capabilities are very rigid. You can't create your domain and subdomains, and certain users can't create domain and subdomain. It's all the system administrator has to do it for you. And the schema is rigid. That's why you have very complex schema upgrades. And I would say that whether it's for programming languages or databases, all this complexity is due to what I would call system myopia. People don't look at the whole system. They look at their small part of it, and they will optimize that small part of it at the expense of the overall system. I have this saying that a programming language without good data persistence is only for toy computations about irrelevant data. If you don't care about the data, that's where your programming, yeah, well. And conversely, a database without a good programming language built in is just for toy data that is not part of any relevant computation. And today we have programming languages and databases that are essentially to build irrelevant systems. They are not designed to be part of a system that makes sense. They're just optimizing their small bit of the system and making everything else harder. So what would a programming model for orthogonal persistence look like? Well, I will start with, we don't want transactions. Why? Because transactions is where you start transaction here up till the moment that you as a programmer commit, which means that you have global knowledge of everything between the point when it starts and the point it ends. And code that uses transactions doesn't compose. You may have tried. You'll find that it doesn't work because it requires global knowledge. And when you compose, you want to compose things that it require local knowledge. If your transactions are too small, instead of having a 5 gigahertz computer, you have basically a 500 hertz computer, because there's nothing that happens while you're between every transaction that takes a few milliseconds. So whoops, you have a very slow computer. If your transactions are too big, now there is always a conflict between transactions, and instead of having a 10-core computer, you have a 1-core computer, because there will be only one core doing anything useful at any point. So transactions are bad that way. Transactions, they are needed at some level in your database, at a very low level, but they are totally the wrong abstraction for anyone to use above this low level. And the reason why these transactions are necessary in today's architecture is because processes don't persist. And therefore, you always have to think about your program will die at any point, any time, so you have to think all the ways the thing, you have to maintain global correctness invariant for everything. And that's why you have transactions, that's why they're bad. But if processes persist by default, suddenly you can have untied transactions, or how I like to call them, critical sections, which basically means don't transact here, or don't look at this data while we're here. And because and the way it's done, it's been invented by Dijkstra in the 60s, I think, or something like that. Well, you have a lock, a semaphore, or something, and while this semaphore is held, other people will not look at the data. And this is a totally local thing. Yes, the critical section itself has to be small, but the code that uses critical sections can be arbitrarily large. It can compose. And the knowledge about what is protected by the critical section is local and not global. This is composable. This is a high-level concept. It is already used and everywhere. If you have a language that works with threads or multiple cores or any kind of concurrency, you already are using critical sections even if you don't know it. It just works, it's composable, it does everything you want, and it works because processes persist. So if I have end-to-end transactions and critical sections, what happens to commit? There are times when you absolutely want to not send the money before you have saved the data. Otherwise, the bad guy will have you send the money, kill your computer before it has saved the data, have you send the money again, and repeat, and he'll get all your money because you're too stupid to persist your data before you send the money. But this is a local constraint, and it can be easily automated. Once again, there's a technology that everyone uses all the time. Anytime they use a language that supports multiprocessors, threads, etc., it's called a memory barrier. You already use it, even if you don't know it. It's just that this part of the code will wait for this bit of memory to be committed to, to RAM, in this case, before you go further. Except now, instead of just committing the data to RAM, we'll commit it all the way to your 5 data centers. Who here manually flushes his registers to level 1 cache, or his level 1 cache to level 2 cache, or to level 3 cache, or to RAM? Nobody. Why should you manually flush your RAM to disk and your disk to your 5 data centers of backup? Of course you shouldn't. This is stupid. Once you have orthogonal persistence, it just works. You have a high-level concept of memory barrier already used. It just works. With respect to domains, you can work with any data model, with any execution model. If you care about speculative transactions, whatever, you can implement them on top. No problem. It's actually quite easy. It can work with any programming language with minimal changes. You just add this notion of critical sections and memory barriers. There you go. You add 2 primitives to any language. There it supports orthogonal persistence. Well, there is slightly more when you need to deal with schema upgrade. You still want also to support schema upgrade and other things. But for the orthogonal persistence itself, you just need the critical sections and the memory barriers. The identity of domains are not tied to a disk, machine, vendor, etc. Therefore, your domains can actually persist for your whole life and beyond. And of course, joining subdomains, doing data federation, have a consensus between several domains, or duplicating your domains or sharding it over several vendors should be a basic system primitive, not something that you do the hard way for tens of millions of dollars. So here's what happens for orthogonal persistence once you have it. What happens to these other issues? Well, you never save and copy anymore. There's no save, there's no copy. If you use them, you go to jail directly. Instead, you have publish and share. So where you wanted to save a version to say, this is a version I want to share, well, you tag the version as stable, and then you share it. Where you used to copy something because you want to modify it, well, now you fork a version, which means that you have some kind of version control integrated in your system. You never copy and send, you just publish and share. And if you're on the other side, you never need to forget. If someone made a comment on your blog, they can't erase it. You can erase it if you want for yourself, but you can't erase it for them, and they can't erase it for you. Everyone keeps their memory of what they have all the time until they don't want it. Today, the giant spy corporations know more about your traffic than you do. If there's a page you watched 5 years ago and you want to go back to it, it's gone. So if there's something incriminating there, the bad guys know about it and can incriminate you. But if there's something good about it that you want to remember, it's forgotten. With orthogonal persistence, the opposite can be true. You never need to forget anything. And the bad guys, hopefully with encryption, don't need to see it. You never need to get out-of-memory errors. Instead, you will manage your quotas. Today, one program goes wrong on your computer, the entire computer grinds to a halt, and it crashes, and basically after 5 minutes you decide, okay, I'll reboot it. But in an orthogonally persistent system with domains, when the domain goes over quota, it can just stop, and then you escape to the meta system and say, what am I going to do? Am I going to just increase the quota? Am I going to garbage collect the data? Am I going to, oh, there's a bug that leaks memory. Am I going to fix the bug and restore it? You can do that. You can do that from outside the system because you have defined what is inside and outside the system. You have tied your data to your processors to stay together and therefore can be debugged together, which cannot be done today on Unix, Windows, or Apple. You can predict the usage. You can anticipate the increase and provision, etc. And all that is possible, once again, because you haven't forgotten the correlation between the live code and the data. One of the main architectural design principles that I followed across my career is that the best way to find correlations that are hard to find in current systems is just to not forget them to begin with. Because this correlation is usually there at the moment you create the process, at the moment you create the data. If you just don't forget it, it's there when you need it. But if, like in current systems, the first thing you do is drop it, which files correspond to which processes don't know, then it sucks. It's very hard to reconstitute that afterwards. You never need to migrate. You can just upgrade and reconfigure. Today, you know that you will need to do upgrades because your schema will get obsolete, your backends will get obsolete. But in a language, in a system with orthogonal persistence, you will have schema upgrade support built into your programming languages, built into your testing frameworks, so that whenever you test software, of course, you test the path of schema upgrade from the previous version, et cetera, et cetera. When you reconfigure your backend, you will no longer have lock-in to hardware, software, or vendor. And all this is normal operations. This should not be $10 million projects. It should just be normal operations that are part of every programmer's cycle. Another point is that today people like to write programs in C or C++ or low-level languages because it's faster. And yes, it's faster, and if that's what you want, you should still be able to be faster, but you will want to do that inside a domain, a virtual machine that is isolated from the rest. You will want it to have built-in versioning so that the day it inevitably gets corrupted, you can resume from a safe, correct version. So you don't have to sacrifice your crazy fast but incorrect languages and your undefined behavior exceptions or whatever. You can still have your C and your C++. You will just run them into isolated VMs. Because one thing that you learn when you have an orthogonally persistent system is that it's a live system where you want to cultivate the data in the long run. Your data is not just throwaway data from a dead program. You run it, it dies, and you throw it away. No, your data is live. There's a reason it's there. You will still care about it later. And so if there's any chance it will get corrupted, you will want versioning. OK, conclusion. My thesis was that orthogonal persistence is the right thing that everybody expects, that persisting continuations or processes is what simplifies everything else in the design, that transactions are the wrong abstraction, and that orthogonal persistence solves many problems and elevates even the problems it doesn't solve. That's the technical thesis. But as you saw, I started talking about reflection, capabilities, versioning, upgrade, schema upgrade, and consensus, all as basic things provided by the system. This is a pervasive change in your entire ecosystem. It's a boil the ocean thing to reduce the world from our friend Curtis here. It's also a change of mindset from programming languages to systems, from command and control, I tell you something, you do it and it's thrown away, to I'm interacting with you as a computer and we have comparative advantages of what human and computers can do, and it's a much more interactive mindset. And of course, you can still run legacy code, but in managed VMs. This means that there will be new markets, a total change of business models. You don't have apps, you have documents and extensions. You have local code, and you don't have app servers that spy on you and advertise to you. You have competing blind storage providers or competing blind execution providers, and you don't have monopolies on apps that are vertical and control everything you do. The admins will answer to the users and not to the app vendors. That changes the entire market dynamic of software. I think that overall it's a better division of labors. The users are empowered, since they don't have to deal with this persistence nonsense. They can refocus on the things that matter. And they are, of course, the ones in control to the admins they can delegate to if they don't want to deal with that. The developers don't have to implement 1,000 file selector, the 1,000 color picker, and whatever services that already have been done 1,000 times badly. They can specialize on the one thing they want to do and they care about and they are good at. The providers are no longer vertical monopolies, and the defenders of software, again, bad guys, can control smaller attack surfaces and more easily find the bad guys. So I believe that's a much better division of labor. The conclusion is that orthogonal persistence time has come. There is durable execution now. I see people in the audience who've been working on it. Thank you. It's great. Today is only for backends, I think. But it could be for everyone, everywhere. And whoever will make the first orthogonal persistent system usable by average user will redefine the industry. Like it's $1 billion opportunity or multi-billion, $100 billion opportunity to redefine the industry. I have a semi-formal description of the orthogonal persistence model at this URL. I have a blog where the first chapters talk about that. I have an X Twitter account. Please contact me if you are interested in all the opportunities regarding orthogonal persistence. Thank you, and if we have time for Q&A.
Thank you, Farah. I think we have time for perhaps one or two questions, and then we're off to the break.
How do you envision handling application-level cryptography use cases that need access to offline signing and local entropy that is the exception to wanting stuff to be orthogonally persistent? And relatedly, did the one-time pads, do you envision them coming from a personal secure signing device, such that you can move from device to device, you have a new password every time or for every domain?
I think that's another aspect that can be used, defined reflectively. So if you have a reflective architecture, there's not one aspect persistence that is handled by orthogonally by the system, but you can define more aspects that are also defined orthogonally by the system. And so encryption could be one of them, the file selector could be one of them, the color picker. Everything that today is done as a library or a software element that everyone rewrites their own way could be instead done as a system service presented in a reflective way. And the reflective way ensures through this full abstraction that the people using it cannot cheat by looking on what's inside or make bugs by doing what's inside badly, whereas the people who do what's inside cannot cheat by trying to spy on what's going above. And if they do a bug, it will be the same bug for everyone, which will be easier to find out. So that's why actually follow me for more on reflection and not just persistence. To me, orthogonal persistence is the most salient aspect of a wider reflective architecture. Last question.
All right, thank you folks very much. We'll have the
Everything
break
is
after
clear.
this.
Thank you.